Hello, my name is Chris Ryan. As many of you are, I'm a software engineer specializing in C and C++. I prefer C++, but occasionally C is necessary. Today, I'm going to give you an introduction to binary object serialization with data structure, traversal, and reconstruction. It's basically a mouthful for saying, I'm going to take blobs of data, write them out to a stream. The stream could be a file, a socket, whatever, and then how to turn around and read those back in and actually make objects on the fly, reloading them. I'm not here trying to sell you on the idea of the using my serialization. I'm here to share ideas and techniques that I use to implement it, and hopefully that you might be able to use some of those ideas. You got a little bit about me, a little bit about serialization. We're going to go over the techniques I'm used to implement this. Most of the stuff I'm using is compatible with C++ 14 and 17. It's going to be using a lot of function Template Argument Deduction, and SNF going to talk about how we stream out objects, pointers, arrays, traverse through the hierarchy, and then reconstructing the data. And if we have a little bit of time, I'm going to tell you a little bit about the different mechanisms you can use for streaming the data in and out, the data sources, and a couple extra bells and whistles. I'm also going to tell you about how you can switch between using SNF methods and convert those into C++ 20 concepts. And I have a couple screen grab demos, not live demos, but some snapshots of what I've done. This is me, software engineer, a lot of noise on the screen. Basically, I've been doing C++ since the early 90s, C since the late 80s. I've been everywhere working for everybody around the Seattle area in lots of different industries. Like I said, I'm not trying to sell you on using my library. I'm just trying to teach you what you potentially can learn. This was my personal learning exploration of, can I do this and how can I? I attempt to keep my code portable and platform agnostic and mostly C++ standard compliant. There is a lot of code in these slides. There's a lot of slideware that's in here. Not all of it is exactly what is in my library, but you should get the idea from it. Most of the slides are not that dense in code. There are a couple that I'm going to try and walk you through so you get some of the ideas of the internal mechanism. And I went over a lot of this already. A lot of serializations store data out to binary or to text-based formats like a JSON. I consider a lot of those very text bloat and conversion heavy. With what I'm trying to do is save in a very compact binary format. And then these mechanisms are agnostic to what type of media you're loading or saving from. It can be a file, to a memory, a network stream. A lot of other serialization mechanisms are very intrusive into classes. Mine's minimally inclusive, and I'm not using any macros. A lot of the others are using macros, and that just hurts me. What you're going to see is not production level code. I mentioned the slideware. Some of it, I did some funny formatting to fit it on slides. I've omitted error handling for simplicity. Generally said thread safe, not guaranteed though. I mentioned there's other serialization techniques that those tend to be text bloat. My introduction to binary serialization was through Microsoft Foundation classes in the early 90s. A lot of people really, really hate MFC, mostly because it's the Microsoft product from the early 90s. Even though it was actually way ahead of its time in a lot of ways, did a few funky things, but it actually was very good for what it did. And this is, again, is a, how can I do this? and I was mostly just a personal project. If you want to use pieces of this, you can. I will be pushing this up on GitHub shortly. Okay. Binary object serialization, hierarchical data. If you have a set of data structures, you can traverse through them just by climbing them like a tree. I'm just going to go down and do a left, right, or left, me, right for streaming this data out. And everybody knows how to traverse a tree. That's pretty straightforward and simple. It gets complex when you get a data structure that points back to itself and other members and then loops. There's no way to cleanly climb through this tree without at some point getting lost or in a loop. What I do is I do object tracking. As I serialize something out, I remember that I've already serialized out and don't repeat that. So I'm not going recursive through this and traverse back through the whole rest of the system. Okay. In a class, or even just in general, different data types. You have an object, which may be a simple plain old data type or a complex struct or class. You can have a pointer to an object, you can have an array of objects, or you can have a reference to an object. Now, what can we persist out and reload? We can save out an object. We can save out a pointer, which means we need to reconstruct it when we reload it back in, and then an array of objects. We can do that. A reference becomes complex or complicated because an object or a reference must be initialized at construction, because we loading existing objects, that's going to be impossible to do. So we're not going to bother with serializing in and out references. The other issue is we can only serialize out objects. Well, we can serialize out anything, but we can only serialize them back in and load the object if it's non-const. I don't want to break rules and cast away the const on an object just to reload it. That is violating the rules in so many ways. So objects can also be strings, vectors, arrays, lists, shared pointers, and the different intrinsic types like ints and floats, and or your own homebrew classes that you've made. Now here's a frequent serialization style that some of you may recognize from other things, very similar to the boost mechanism. You create a data source, a file, you load it into an archive object, and you stream out your data you're saving. To load it, you create a file or open a file, load it into an archive, and stream into it. Each class that you want to serialize will have a serialize function, and it can basically determine, is it storing? It serializes out each of the members. Is it loading? Then it can stream in each of the members. Each of these member data could be other complex objects. So this goes traversing down through the tree, as we've shown. Also, if it was a complex object, and say that data was a pointer, we can traverse through the tree and go into that recursive reentrant network data structure. When I say network, it's a graph. And then we can protect ourselves from reloading data on there. The archive, to get hold of each object when we go to stream it in and out, I have a friend method that passes the archive in and a reference to the object type. And then we turn around and tell the archive, because here we're in a friend, so we're not in the archive itself, but so we call the archive and tell it to save it and then return the archive. That's just standard stream nomenclature. So when we go to save the object, we need to save the object of the type that we're dealing with. So I mentioned we have the type itself. We basically have a reference, and the reason we use a reference is so we can read in and out of it. We also have a pointer to a reference to a pointer, so we can fill in the pointer or read from the pointer, and then we can save arrays. So we need to determine exactly how we're going to save those out. Let me let's get back a little bit here. Each of these types, we're going to need to have a specialization for the different types we're going to want to save out. The way we do specializations is SNF and A. Substitution failure is not an error. I list C++ 17. That really started sneaking in 14. And I think you could do some simple types with 11. Very few compilers by default start at 11. So everything I do runs in 14. So we have, if it's an integer type, basically I just checking the type traits. If it's a integral type, if it's a plain old data, is it a plain old data type, but not an integral type? And the reason I do this is when it's an integral type of an int or a long or whatever, I actually going to store it out in network normal form. So you can read it in on a platform that is big Indian, little Indian, different from yours, and your values will still be the same. I use the terms plain old data here and is pod. As you get into C++ 20, that term has been deprecated, and it basically needs, there's several different is trivials that need to be done. Now, if it's an object that I want, that's a complex object that I've built, I have two forms of has serialized and is serializable. I'll get into a little bit more detail on those soon, but you saw in the previous example, I have a member function. It's called serialize. I examine the class and I look to see if that class has a serialized function. This is a home built type trait for my classes that I can interrogate and ask it if it has a serialized member. The serializable, we'll get into a little bit more detail later, but basically it has its own serialized and it can handle virtual mechanisms in the serialization, and also handles multiple layers of inheritance in objects. So here's these types we were just looking at. Is it integral? Is it plain old data? Yada, yada. And then SNF is, you'd say, you do a template of the type. You say, enable if this type is integral, or if it's plain data, or has a serializable. And you would just call each of these appropriate saves. A little funky thing about enable if that I don't like, but it's part of the mechanism. The void here that is in the enable if is the return type of these functions. That's just part of the way the mechanism works. When it's going through trying to match each of the different methods with what we want to serialize out, if the type is not an integral, this entire section does not exist. And so it's not going to be a candidate for linking or binding with it. Same with plain old data, and then my has serialized and serializable. That on this slide, it creates a little bit of extra noise in my class, my archive class, which is extra baggage that I didn't want to do. So I created my own template mechanism where I take the enable if and combine this up. And so I say if integral type, if plain. Notice these are is and these are if. So instead of doing the enable if here, I just say if this, then this, if this, then this. And hidden inside of it is the return type, which is what I actually am passing in. All right, it's defaulting to void, but if I wanted to, and it was some other funky return type, I could put those in here also. So this is how the archive reads. Now these are the generic types of, if I'm actually dealing with an object of each of those specializations, drilling down a little bit on that, how that would actually look, is I would say if interval type, the function save actually goes to save the data out, it adjusts the byte order and writes it out. Reading it in, I have to have an empty type of that to read it into. Then I swap the byte order and store it back into the data, the reference here. Same for plain old data. It's doing read and write. I don't need to do the byte swap on it. Has serialized and serializable. It just calls the serialize function on the class that I'm trying to save out. And it can be the same one, but later sniffing dealing a layer down will also have the has serialized and serializable. So those mechanisms will break out in further detail. The others were if it's a reference to an object. This is if it's a reference to an array of an object. And a nice little handy way of templating, you can do the type and have it deduce the size for you. So I get a reference to my array and I know the count. When I'm saving the data out, I save the count out to the stream and then I iterate across all the elements of the array and stream them out. When I go to load it back in, I load the count from the stream and then verify that the count in the stream and the array size of what was deduced is the same. If it's not, it's an error and means my code had changed someplace. Then I iterate across the elements of the array and stream each of them in. That just as if you had yourself said, stream out one, or the object sub one, object sub two, object sub three. Okay, this is very similar to what we saw before. Set up a file in an archive and I stream into it, or stream into the archive from my class or reload. And this is if my class has a serialization function, says it's storing, it streams out, or streaming in. That's relatively simple to understand. Normally when you're dealing with archives, if you archive a pointer out to a cout, it will actually just take the number and spit out the number of what the value of the pointer was. We don't want to do that. My archive mechanism will actually realize this is a pointer, and we're actually going to save it, telling it in the stream that it was a pointer, and then we call the serialize and do this, is save or load exactly the same. When we go to stream it back in, I have an empty pointer, a null pointer, and I stream into that. There's nothing to stream into at that point. The archive mechanism reads from the stream and says, I'm expecting to read this type of object, and I will construct that object and place it and stuff it in the my class pointer. And then then once I have an empty object, then I serialize into that and read the my data. That C is an error there. That should not be a CM. It just should be a member pointer. Now, if you have classes that are derived from each other and you're going to stream out that data, this side looks exactly the same. But this is a my base. So if I were to just directly call the serialize on my base, when I go to save it out, I would only save the data from my base. So I need to have a virtual mechanism for here such that it calls off the most derived type. It does its streaming and then drills down and calls the base. And the way that it knows about the type information of what the type of object is it's going to store out is I have a CRTP, a curiously recurring template pattern, that I use as a base class for a serializable object. This has some mechanisms we'll hit in a little bit of future, but part of that is it declares serial as a virtual, so it automatically inherits the virtual here. So when I go to stream it out, it calls the serialize here, and then it stores out the data, drills down, and does the base and saves out its data. It's not specifically important that you drill down to the base before, but as in construction, when you construct an object, it's like an onion, it's going from the inside out. So therefore, it's better to drill down first, just in case there's any of your derived data that is dependent on base data. Also, in the multi-layer, I also have used the same CRTP mechanism for having a serialized object for my derived, and I tell it what the base is my base. So it knows in the inheritance hierarchy that my derived is from my base. And you'll see this here in a little bit, but serializable actually introduces a base class above my base, and it actually injects a class between my derived and my base. This serialization mechanism keeps track of what the type of object it is that's being serialized out. So when it serializes out, it saves the type of this object. So when it goes to serialize it back in, this serialization mechanism knows what type of object to construct and put in this place. Even though it's a my base, we're going to construct a my derived object and then serialize into that. A pseudocode of how if serializable, remember, this is the one with the multiple layers. And I store the object ID. If it's the very first time that object ID is saved out, I save some reconstruction information about that ID out. It knows if that pointer has been loaded, had been saved out before. And then I stream out not the pointer of it, but a dereferenced pointer, so the actual object itself. The whole archive serialization mechanism goes reentrant at that point. It does analysis on what the type of object this pointer is, and then does its appropriate serialization. When I go to load it, I load the object ID from the stream. If the first time that object ID has been loaded, I load the type ID information from the stream, a little bit more about that later. Then I dynamically create the object, and then I store that away in the object map, and then I stream into that. If it's not the first time this object has been loaded, when I save this away in the object map, I know I've already loaded it. I don't want to load it again. I just get the object ID from a map that I kept track of when I loaded it the first time, and I just assign that pointer. Nothing to serialize in or out if I'm loading something that's already been saved. Just a handy tip for people, C++ does not have an implicit base pointer. I like declaring a base type. So later I can just say base, calls down the serialize, and automatically calls the serialize function in the base. A little shortcut on here, when I'm doing this using on the base, I do not need to include all the declarations and the specifications of this type. It knows I'm derived from this. It automatically knows to use that. I could have done the pointy bracket, my class in there, but why bother? One reason why it's handy to always use a using on this, if someone comes along later in some other class, when you have a multi-layer inheritance, and someone changes or injects a class in the middle on you, all you have to do is update what the base type is, and you don't have to go through every one of your functions that's attempting to drill down the call of the base. It just automatically knows base, call down to the base function. Okay, so if I have my class and I've serialized it and I have a serialized function, I derive from the serializable and tell it that it's a my class. This injects a template underneath me. It's called serializable, and it chains from the base. By default, the base is a serializable base. In the serializable, oh, actually, let's skip a little bit of information here. I'll come back to that. I said that I wanted to save out type information about the object that I'm going to be saving. I need to know effectively what the name of that type of object is and a way to recreate it. So I save a pointer to member function to construct my object. And also I save a hash. The hash is a shortcut of the name of my object. That just stores it away. I get the name, I hash it, store that, and I just store to the pointer to function to create that. Where do I get that pointer to function to create it? Oh, that comes in here from the type info. It's a static member of my base, but it's tied off of the base, the type of my derived type, and I have it construct the type info with passing in their name and the create func or pointer to function. This is also a static member of my serializable base or my serializable CRTP. And basically all it does is I call this and it would return a new of my derived type. I have a layer under this, it's called serializable base. You cannot have your base anchor virtual function in a template, because if you want to use a polymorphic mechanism, you have to have a base pointer of a concrete class. And if you can't have a pointer to a template or to a base template function, because that template name is different for every instance, or not every type of that object. So therefore, this is a actual base class that has a virtual. Anytime I want to reference anything that's derivable from one of these, internally I reference it in my archive as a serializable base. So I don't need to know the type. The polymorphic mechanisms all work in the way they normally would. The type info has a static map, as a static function of a static map, where I store away all this type info. When I want to find an object to recreate, I have a static function that I ask the static map to give me back the hash of that object, and it gives me the type info. This will become apparent in a little bit of why this is interesting. Going through, showing you a little bit of spaghetti here, but the hierarchy here. My class is derived from a serializable CRTP of this, which has a type info in the static member of the serializable that's a type info, which creates a type info object that stores itself away when it's constructed in the hash. And so my type info is dynamically constructed pre-main. So all the data is there for every class that is serializable. You don't necessarily need to serialize every single function or build serialization into every single class in your data, but only those that you're actually going to save out. So your entire application doesn't have to have these, only the data that's important to save. So we saw something very similar to this already. This is using serializable. So this is my class, doesn't derive from anything. However, internally serializable, it does. It uses that serializable base. If it's a multi-layer serializable inheritance. This is just what we described before. The CRTP points back to my own object, and then it also points to my base. My base is also a fully serializable object, so it also is serializable to my base. So internally, this is what effectively gets constructed: a serializable base with a serializable template of my type of this type of base. I have my base class with the CRTP, the template for the serializable for the type of my derived, and the base class of my base. And each of these has, I got a serializable here and here, in addition to the hidden base serializable. Because they're make sure I say this carefully. This template by default would do a serializable base. However, since I specified what the base was, it directly calls to here. There is not a serializable base between the two of these. It inherits all the way back up the chain to what serializable base is. And this is just kind of what I just talked about of the different types and where they reference back up the chain, so you can see how the inheritance works. I'm going to speed up a little bit here because I'm running halfway through my time and I still got quite a bit more to go through. So we talked about we have a file source or different data type sources, create a file, load it into an archive, and stream in and out of it. This data source is anything that I want to derive from that can load and save. I had been given examples here of a file source. The constructor will go out and create a file, and then I can load and save from it, and it reads and writes to that file. I could also do a data source or socket. So we got our base object, load and save. I can open a socket to act as a client. I can open a socket to act as a server, and I can do in my archive, I can load this base data source into my archive and stream in and out of it. It doesn't know that it's talking to a socket. However, on opposite sides of the application, one streaming in and one streaming out, live, two different instances of the application, they can communicate across the network. So this is what a socket source would look like. I say the socket that I want to serve out, I give it the port, load it into an archive. Here I create a socket, tell the server I want to talk to in the port, I load it into an archive. I can stream out to this. This also gives me the advantage, or then I can stream in. Notice here I'm streaming out and then streaming in. I can take this, have a response class, construct a response, and turn around, reverse the stream the response back into the archive, and turn around and read it back in. The bidirectional stream. And just for the sake of demonstration, the send returns the response back to whoever called that, and the receive also has the response. Here I have the empty response. Here it's constructing the response based on what the data was it received in. I also have different layers of filtering you can do on a data source. You could have a data source, pass it into a filter source, and then pass that filter source into an archive. And one super simple example of that would be encrypting the data with, and this I'm just doing a simple mask where I XOR the data. So I encrypt it, and I can change this mask later in the middle of my stream to show that, or to encrypt the data and then change the encryption. And XOR masking is not very elaborate, but you could use a full public-private key mechanism for fully encrypting your data. Everything that gets written out gets run through and chained together through these The save masks the data and then chains down to the base, which would then be the file source or the network stream, whatever it was. So this is how that would look, or the extra bells and whistles. I create a filter, I give it a key, I create my archive, I stream out. Another thing I have is while I'm streaming, internally the archive keeps a checksum. You can use a more elaborate checksum if you want. I'm just doing a plain sum. When I create a checkpoint, I actually save out what that is. And here's an example of I changed my key. I just increment it to the next value of what my key is and continue streaming. And I do another checkpoint. The data here is encrypted with this key, and the data here is encrypted with this new key. When I go to load it back in, I have to know the same key running through the same filters. I go to stream it in. I check the checkpoint and I see, is all the bytes I've read in match the checksum of what the file thinks it is? Because in the stream, it wrote to checksum is, I read everything in, I've added that up, I check it. If the checksum doesn't match, I just return a simple error. Grin, I said I don't have good error checking in this. Real implementation of this would probably do some better form of exception handling. Again, then I continue reading, I set the new mask, and I continue reading in, I check the checkpoint again. It needs to be mentioned, when you stream out in binary, you have to stream out exactly everything in the same order as you're expecting to stream it back in. A optimization that I do, because I have a lot of integers that I stuff into the stream for object IDs and pointer IDs. I don't want to always stuff a 32-bit uint into the stream. So I did a compacting. If it's a small value, I store it out in 1 byte. If it's a larger value, I store it out in 2 bytes, and I keep streaming this out 127, 0 to 127, the bottom 7 bits over and over again until I run out of values, then I put a stop bit in. So these are the values, the numbers that I can store. I guess this is similar to the stream mechanism that some other people also use for a variable dynamic size uint. I can't remember what they are, but last time I gave this talk, someone brought one up of those. This isn't really important. It's just a handy little trick to use sometimes. Okay, all the different object types we can save in. We handle everything that's different integral types, plain data, has serialized, and if it's serializable. A point I wanted to bring up, which I should have made more clear earlier, I talked a lot about the serializable. That's the multi-layer inheritance with the CRTP. If you do multiple layer inheritance, potentially serialize out from the base pointer, you need to use this serializable so it knows to handle the virtual and the reconstruction. If it's just a class that has a serialize, it doesn't need all that type information. It just hierarchically calls the serialized member of that class. So I can load and save if it's an object, I type a pointer to an object, an array of a type. I also have all the different member specializations. If it's a shared pointer, unique pointer, vector, special case array, just iterate through the list or iterate through an array. If it's a map, I stream out all the keys and all the map items, and we'll head a little bit more detail on that in a second. If it's a string, I also handle if it's a char array. It's a specialization of a integral type. I store it out rather than streaming out each character at a time. I actually just store that as an array of a blob. I also have, if you have something that you can't save out through normal serializations, you have a blob of data in one of your classes, whatever it is, it could be a bitmap image, whatever, you can actually just take that a pointer to that and save off the size yourself and then stream it back in the same. Just pre-allocate what that size is. The sizes that you stream in and out have to match up. Okay, so what if you have a complex object? Say you had a map of strings so the strings mapped, or pardon me, the map between strings and vectors, but this vector was really a shared pointer of my bases. So you could actually read the name of this would be a map of strings to vectors of shared pointers to my base. The type deduction will take the object and peels it like an onion from the outside in. So it knows this is a map. So my key and my value are automatically deduced, where the key is this type name and the value. And I would just, when I call my function for save map and key, then for each item in the map, I just do a for each basically. And I take the key and I have the vector in it. I save the string. It's a string. It knows how to save. It goes reentrant into the serialization mechanism, saves out the string. I save out this, the value of this is a vector, which calls my vector serialization mechanism. The onion gets peeled again on that typo. I don't know where that S came from. So the type of this is a shared pointer of my base. So therefore I go reentrant and I serialize out the shared pointer, knowing that it's of a my base. Then if my base, if it's serializable, it calls using the serializable mechanism. Because this was a my base that it was saving out to, therefore implies that there was a my derived, like we saw in the previous slides. And so it would call the polymorphic mechanism on serializing that out. This also, the same peeling works for serializing in. This is what we talked about. If it is non-derived, I can just call, when I know there's an object of my class, I can just directly call the serialize from inside the archive on this object, and it saves its data out. And it goes reentrant on whatever data types those are, storing those in and out. I got the my base and the my derived. Normally, as we saw, you can't just inherit straight from this. But you don't actually have to always say is loading, is saving. The archive itself knows if it's loading or saving. I can just say archive, save out, or serialize this data, archive serializes. If it's loading and saving, it automatically does things in the right order. And rather than using the shift stream in, stream out operator, instead of just saying serialize, I can say and, or and. And this is very similar to the way that the boost serialization does it. Internally, it calls a serialized function on that data, and the whole system goes reentrant. Okay, for C++ 14 and 17, I used the const expr enable if mechanism. If you're going to do template, or if you're going to do concepts, it reads a little different. Instead of doing the const expr, you have to declare a concept of an integral type, and I say is integral, and I have my some plain data type has serialized, and this is an extra logic step I need, and then is it a serializable type? So rather than doing all of the ifs in there, I just declare a type and I say save serializable type, or save serializable type pointer, and then save serializable array. Got a couple examples here. Say I'm serializing out okay, I mentioned that we can handle shared pointers, an internal mechanism that I didn't draw out before. Shared pointers are very much like pointers. You can have multiple objects pointing to a pointer, and we don't want to stream that out multiple times, and we don't want to turn around and stream that back in. So a shared pointer internally knows that there's a pointer to whatever object I'm pointing at. I serialize out that it's a shared pointer. I serialize out the inner pointer of what the object is I was really pointing to. I save that inner pointer in a shared pointer map. So when I turn around and also read it back in, or when I continue reading it, streaming it out later, if I hit that same object, I just give it that same object ID from the shared pointer map. When I'm streaming back in, if it's the first time I've hit that shared pointer object, I serialize in that object, stored in an internal map. And so I have an entire map of shared pointers. Next time I hit that exact same shared pointer, I pull it out of my shared pointer map and stuff it back in so it's properly ref counted internally. So here's an example of serializing in and out a tree object. I have something that generates a tree. The root node on that is a shared pointer. I stream it out. And this is in the same application. By closing out the scope here, I've destroyed the shared pointer. I've destroyed the archive. The only place this exists is in an ARC file. I open the file. I go to stream it back in. I have an empty shared pointer of my type node. I stream in and I spit out the tree. This is what it looks like, or this is what my node looks like. I have a shared pointer left and shared pointer right and some data. And then I call serialize and I just say serialize out or archive the data, the left and the right, because of the shared pointer, it automatically traverses the tree. And this is what I have a draw tree function here that climbs the tree and draws a text version of the tree. And so this shows this is what I'm serializing out. The object, went into that scope, the file was closed, the archive, the shared pointer, and then I just stream it back in and I get the same tree back in. If I have a multi-layer instance of this, I got the node, or my node, I have my base, and then I have a derived. And in this example, I just have the left and right pointer of my tree in the base, and the derived type has what its data type is. Serialize it out the same way. I just say, serialize the base, it serializes out the left and the right, and then I say serialize out the data. And it's exactly the same as before. It spits out the tree of what we were saving, and then shows that it reloaded it correctly. A little bit more complex example, if I have an application that both reads and writes from the stream, my main starts a couple threads. One's a server, one's a client. In the server, I construct what the server object is going to be in the archive. I start a root node of my tree. Each time through this loop, I'm going to add an extra item to the tree, or stream out the tree. And when I stream it back in, I'm going to add an extra random item to the tree. On the other side, it goes to stream in. It's an empty empty tree. And I stream in, or what was streamed out here. I insert a node here called client and pass it back and forth. So these client and server are playing ping pong between each other, each adding items in the tree. This little redirect, the text that's spit out here shows that the server's talking and the client's reading, or the client's talking. So you see client server, server client, client server, yada yada. And this is a random tree that was built, and it's that the root was created, and we got the client. It added an item, and the server added random. And because this is a sorted, inserted tree, it's just wherever these things happen to be where they got inserted by the sorted order. So it's the ping pong back and forth reversible socket.